for MemSQL. Prior to joining MemSQL, he spent 12 years on the Microsoft team building MemSQL server. So that's a unique background. Please welcome Dmitry Chikatilo.
Thank you. Well, first of all, I appreciate you guys coming tonight. And we started to have with people is great. So, so like Eric said, I joined from the dark side. So I've been running Linux for a number of months already, and I'm very happy using my Mac. So enjoying it very much. So today we'll talk about MemSQL. I joined the company about a month and a half ago, but I've been working with it for prior to that and enjoying it very much. So that's one of the reasons why I decided to join. And also work with one of the founders back 2 years ago at Microsoft. So what's MemSQL? So let's talk a little bit about the idea, how this idea was born, and what was the kind of the driving need behind the scenes. So often we see a number of analytical workloads, and we see people using SQL language for querying repositories of different kinds. So ideally, what we wanted to do is the founders, they wanted to really accelerate the performance, right? So we know that, SQL Server, SQL language in general, SQL applications are very performant, and if you really want to pay, if you really want to make them extremely performant, you have to pay a little money. And that was kind of one of the key motivations for the founders, is to really design a system from the ground up that will be optimized for real-time analytics. In real-time, we mean essentially split seconds, so basically in that time, because real-time has different meanings for different people. So ultimately, you want to really simplify the process, right? So if you're working with traditional database systems, building a system that's extremely performant requires a fair amount of engineering and really expensive, so we want to really reduce it. And ultimately, we want to make sure that complexity of data processing is no longer there. So ultimately, a lot of these database systems that have been born, obviously, in the 70s and 80s, originally they were designed with the goal of keeping the data on a disk, right? And then the query comes in, we want to bring some of this data in memory, in some memory buffers, and then we can answer some of the subsequent queries from memory. But the idea of, designing a system which is optimal for the disk-based data access back in 70s and 80s was a very different idea, right? It was a different idea from what we have today. Today we have very high throughput requirements, high concurrency requirements, and we want to make sure that we design a system that has primary data repositories, not a disk. Primary data repository is actually memory. So that's essentially how the idea of MemSQL came about. We want to make sure that we design a system from the ground up, first of all. We will use all the data structures that are highly optimal for concurrent access in memory. And then later on, we can also use a disk if we need some kind of durability infrastructure, right? So disk is always there. We can use it or not. It's our choice. But ideally, we want to have durability, right? Because, if you want to build an ACID-compliant repository, you want to have the durability component. So some of the barriers that we're trying to overcome with this technology, as I said earlier, this technology is designed from the ground up to have memory as the primary repository for data as well as indices. So by doing that, we will be able to kind of eliminate traditional barriers to performance of data analysis. So just a quick poll here. So how many people currently doing large-scale data analysis? Raise your hands. All right, so quite a few people. So how many people currently running Hadoop and doing some kind of Hadoop data? Great. So how many people feel that they need something a little bit more real-time for some of the queries over the very large data sets? Do people feel there is a need for that? Yes, so that's definitely. That's why, frankly, if you look at kind of the evolution of Hadoop over the last maybe year or so, it's all about performance. We already know we can query massive amounts of data, petabytes. Now we want to increase the performance. This is slightly different approach, and this approach is really kind of designed from the ground up for performance. So by doing that, we will be able to eliminate some of the barriers to enter this business. Is basically we no longer will be reliant on disk I/O, and that's kind of a big thing, right? because disks are getting faster and faster. Like right now, you can get 200 IOPS very easily from a very, moderately priced disk. But ideally, you really want to eliminate completely the IOPS, right? And data access in memory is much faster than data access on the disk, regardless of, what kind of data structures you use, regardless of what type of IO you use. Ultimately, memory will be always there, for much faster access. And also, we want to make sure that we eliminate complex licensing. And again, I'm not the licensing guy, but this is the software that was developed, and obviously at this point we don't have a free version, but we're thinking about doing that. But right now we are really making sure that the software is ready to serve mission-critical workloads. And we have currently a number of customers who are already using the systems in production. So everybody wants to process massive amounts of data, and what's happening when you look at design of probe architectures for very large data processing, you end up with pretty complex infrastructure, because at one point you need to accommodate the data that's extremely fast, right? So the data is arriving very fast, you want to make sure you clear this fast. But then what happens is you have so much of it, so you need to have some kind of data aggregation mechanism, right? That's why people say, well, let me figure out how to aggregate my data. Maybe I create some kind of OLAP infrastructure, some OLAP cubes, or maybe I want to do some aggregation tables or something, right? So ultimately, it's always a trade-off between how fast I receive massive amounts of data and how fast I can actually run analysis on that. So on the speed side, sometimes you can see, the streaming systems, when you have complex event processing, when you basically have like a standing query, and the query is listening to exactly the stream of events or stream of data that's coming in. But even those systems, even though they can process data extremely efficiently, ultimately we'll have to store this data somewhere. So this data is going to end up in Hadoop, or the data is going to end up in some other permanent repository. So we're trying to really bring a little bit of simplicity in this by saying, look, you can actually mix workloads in the same data repository. You can mix your traditional high transaction processing OLTP workload. For example, I would like to do massive inserts, massive updates into my system. And at the same time, I would like to do massive scans, right? So this is my workload for my warehouse. I want to do massive scans for very large tables that maybe, let's say, a billion rows. I would like to do scans on those tables while inserting data, while updating data. So this is where this kind of combination of OLTP workload and warehousing workload come into play. So that's kind of how MemSQL wanted to address this issue by combining things in memory. So this is just another illustration of that. Is traditional data flow is we have a variety of different data. We create some kind of operational data store, right? So what's an ODS? So traditional operational data store is the transient data repository, right? Transient data repository where the data is accessible for querying very quickly. There is not that much of it, but I can actually insert it very, very quickly in small transactions, right? So once I accumulate certain amount of data in my operational data store, for example, over a course of an hour, or course of a day, then I can take a massive bulk load and move all this data into the ultimate destination, my big warehouse, or my Hadoop or whatever. But the separation between the real-time operational data store and data warehousing system always there. So what we're trying to do with MemSQL, we can say, look, we can actually start eliminating some of these barriers because we can have a very fast, very efficient in-memory database that will give us access to data in real time and at the same time allows us to scale. Right? I can show you a couple of examples, but basically I'll show you a simple demo that will show you that the system is extremely scalable and can address kind of traditional scenarios of elasticity. Right? What people want now is people want elastic environment. Right now they run 2 servers, tomorrow they need 5, the day after tomorrow they need 100. Right? So we want to make sure we design a system that will be very elastic to grow the workload without stopping workload and shrinking of the workload if necessary. So by the way, prices of memory, right? So prices of memory right now, the sweet spot is probably around like 8 gigabit DIMMs. But the idea is, right now you can probably get it for like, $150 or something like that. So right now we also see tons of new technologies coming out, both in SSD space as well as in the memory space, that will facilitate the process of storing the data in memory as much as possible. Because people realize that, it's a relying on I/O and distributed I/O like HDFS is a great tool, it's a great scalability tool, but ultimately the speed of access of the data will never be really interactive. one of my favorite conversations was actually with a couple of people from top business intelligence companies that do very high-end analytical tools. But they're all excited about connecting the analytical tools to really large repositories. For example, they connect it to Hadoop, and what happens then is you have this very large repository, and then you have this fancy analytical tool that meant to be used interactively, right? Interactive means that I'm looking at my, UI, and I'm trying to analyze the data. I don't really know what I'm looking for, right? I'm just digging around. And when I'm doing this process of exploration, I expect my queries to return very quickly, right? I don't have the patience to say, hey, I connected my fancy UI for data exploration to Hadoop, and then I start running my exploration, and then every single time I change something, I'm going to have to wait minutes if I'm lucky, hours in some cases, days. Right? This is not really data exploration. So that's why we're really looking for systems and for scenarios where people doing a lot of very interactive querying, when they're looking, they discover, right? Once they discover something interesting, then they no longer need that interactivity. They can say, hey, let me just go fire a Hadoop job, and I can wait till it comes back. So but the idea is, let's try to marry the hot data repository, right? That's basically all my data coming in. For example, I have my trading applications in a trading floor. I have tons of data coming in from a variety of different applications. We put them in a memory repository, and we can do analysis of the data very quickly in real time. So we're trying to marry both hot data repositories and the cold data repositories, and ultimately provide a very efficient mechanism for querying both of them. So let's talk a little bit about kind of how MemSQL works, and it really helps us understand exactly what is MemSQL. So MemSQL has ability to listen to the same wire protocol as MySQL. So what that means is we're really trying to kind of keep it basically as familiar to the business users and business applications on the client side as we can. So the same client-side libraries for MySQL, ODBC, JDBC, for people who like to write .NET, ADO.NET, all the same libraries can be used to connect to MemSQL. But MemSQL has absolutely not a single line of code similar to MySQL. It's a completely different code base, designed from the ground up to be optimal in memory. So when we have the situation that all the tools that typically see MySQL, behind the scenes they will be connecting to this very large, very elastic, very efficient in-memory repository. So obviously the business users won't know any difference. They will think that they're connected just to MySQL. But behind the scenes, we'll have this new revolutionary platform that will allow them to scale the data tremendously and give them very fast data access. So we have ability to scale out, and I'll show you kind of some of the examples how the data is being scaled out. But basically, the gist of it is it's a fully ACID compliant repository. Right? So we have all the aspects of traditional ACID compliant repositories there. So we also have traditional ANSI SQL standard interfaces, right? So the same syntax of ANSI SQL that you guys know and very familiar with is totally applicable in our environment. So if you can take a peek at the technology, you see what are the key benefits and what are the key realities of why MemSQL is so fast, right? We already know we're in memory, so probably data access in memory is much more efficient than data access on the disk. The next interesting technology is actually compilation of the queries, right? Traditionally, when you work with database systems, you write your syntax and then you basically fire it off, and the query engine will receive it. There will be abstract syntax tree and do the interpretation of the query and eventually break it down into a variety of different, query plan objects. So what you do in this case is slightly different. You're actually receiving a query, a regular SQL query, and then you're doing actually a compilation of this query in C++. So first you're doing actually translation of the query into C++, and then you're doing compilation of that C++ code. So what it does is basically creates tremendous efficiency in data access. So it's almost like as efficient as you would write C++ yourself. Except the collections that you'll be querying, in this case, it's not C++ collections, it's just visible to you like tables, right? So the benefit of this is you can get a tremendous amount of performance by receiving the query, translating it into C++ and then compiling the code into native machine language or platform. So currently it runs on Linux, right? 64-bit Linux is our platform, and we basically support a variety of different main distributions of Linux. So what's interesting in this case, we also have ability to strip the parameters out of the query, and in some cases we may generate a couple of different plans. So in some cases we generate one specific plan, but in some cases we may generate multiple plans. And then at runtime, depending on what parameters coming in, we can actually pick the better plan. Right? So because plans may change depending on how your parameters may change. So the idea is, first time you fire a query, you always have to pay a little bit of price up front. So you have to pay a little bit of price of compilation, which in some cases may be just a few seconds. But the next time you send the same query, you will see that compilation basically will be, there will be no compilation of the query, it will be answered from the plan that's already cached, and as a result of this, you have very high performance. So this is just a quick diagram for distributed architecture of MemSQL. So when the queries come in, they start connecting to aggregators. So we have essentially a two-tier infrastructure. So first tier is aggregators. Aggregators are typically the service that's being exposed to the clients. Right? So it can be number of aggregators in a specific setup. So the role of aggregators is really to receive the query, and aggregators also hold metadata. They do not hold any data inside. So the metadata inside aggregators allows them to efficiently point that query to appropriate location in the system. So the system is distributed, so your data may be residing in one of the leaves. So leaves are the nodes that actually will hold your data in memory. So at any given point, you have multiple aggregators and multiple leaves in your system. The query comes into the aggregator, depending on what type of query it is. It will eventually get broken down into multiple requests or a single request into the aggregator. Aggregators will receive the query, they will execute the query, return the results and back to the aggregator. An aggregator may be responsible for further processing of the query, for example, sorting or additional grouping or whatever it might be. And then ultimately, the aggregator will be returning the results back to the client application. So this is just in general, how the system works. So, as you can see here, it's very interesting because right now you can actually build systems that can be combined out of multiple commodity machines, and they can have different memory sizes, they can have different everything, right, frankly. And you can build the systems and scale them out to very, very large data sets. So one of our clients actually out of San Francisco, a company called Zynga. I don't know how many people play Zynga games. Okay, I have a few people are big fans, yes. So Zynga is one of our clients, actually run currently our system in production for about a year and a half, and have approximately 500 nodes right now in production, right? So out of those 500 nodes, I believe about 35 or 35 of them are aggregators, and the remainder of them are leaves. So about 470 of them are leaves. So, and the great thing about a system like that is you have no single point of failure, right? So at any given point, you can lose an aggregator, or you can lose a leaf, or even a group of leaves, and the system will be resilient to data losses. So, and at the same time, each individual leaf node can actually have ability to create durable transaction. It's a very simple configuration file. It has approximately like 8 lines of code in it. And that basically, the file has a flag that says, okay, make my transactions durable. So make my transaction durable means that every time I'm doing a transaction on my leaf, that transaction will get hardened to the log file on that leaf. Okay? At the same time, the magic configuration file, it's also very simple. It has another parameter which is called redundancy. So redundancy can be 1 or 2. If I have redundancy 1, that means I have no duplication of my data anywhere in the system. Right? So in the case of redundancy 1, if you lose one of your leaves, guess what? You lost some data. Right? If it was durable, you can probably later on recover it by restoring it, right, from your transaction log. But for the most part, you lost portion of the data for query. The rest of the system continues to be responding to the data requests, but that one specific leaf is offline. But in some cases, people may not even care. Right? So what if few users of your high-profile application are not responding? not getting the information it's like the rest of the remaining 100 of devices. So that's okay. So if you have redundancy in a cluster of 2, that means that your data will be stored in multiple machines. It will be stored at least on 2 machines, and in this case, if you lose a leaf, you definitely don't lose any data. Right? You will always have a hot standby server that has that specific partition in memory. So this is just a quick general overview of how things work. So if you want to make the system elastic, what would you do? So right now you have the system that has a couple of aggregators and 4 leaves. If you want to bring additional data capacity, just basically spin up another instance of MemSQL, and then you execute a command called add leaf on the aggregator. So when you say add leaf, the aggregator will come back online. Leaf will come back online, and basically the data will eventually be redistributed, right? So there is another command that allows you to redistribute the data. So typically, distribution of the data is not occurring automatically unless the administrator of the system actually fires a command. So the reason why we decided to do that is, in some cases, movement of the large amounts of data. If one of these machines has, for example, 256 gigs of RAM, you may move, a couple of hundred of gigs of RAM from one machine to another. It may be an operation, it may take some time. So the idea is, all the compute and memory resource intensive operations can be monitored by the administrator and modified by the administrator. So let me do this. I will switch right now from presentation. I'm not really a big fan of presentations anyway. I really would like to show you a demo. So we prepared a little demo that we can show you, and maybe we can take some questions after that. All right? So let's take a look. All right. So first of all, I'd like to show you here is, so this is like a very simple cluster that we provisioned, and the software is really easy to use, right? So you basically download the software, just basically install it on Linux, and just set up a couple of configuration parameters, and get up and running. You also can use Amazon Cloud Formation. So how many people use Amazon? Well, all right, there we go. Okay, great. So we have a very simple Cloud Formation file that we can share with you. And through the Cloud Formation file, you can spin up a cluster in just a matter of a few minutes. So here what I've done is basically, I use the Cloud Formation to set up a new cluster. So what I specify here is basically I need to give cluster name, number of aggregators, and let's say number of aggregators, number of leaves, then redundancy in my cluster. Remember we talked about redundancy, 1 or 2, very simple. And the size of my Amazon machine type. So right now we're going to be using, I think, M2 4X large, which has 64 gigs of RAM and 8 cores. So this is the machine of our choice. And this is the licensing key. You can get it from the website. And this is the version of the MemSQL. So right now we're using the newer version, which has more advanced features in it, but basically using a specific version. And now if I can, for example, say test and launch a cluster. So this cluster doesn't get built. I'm just going to make a small one right now. All right, so it's going to take me, I don't know, just a few minutes to get it done. Basically, this is all you need. So after you get the cluster set up, you will get the IP address, external IP address of the aggregator, and you can start creating the aggregator and basically doing the operations. So what I've done here also is I spun up another cluster just a few minutes before the presentation. So this cluster has the following parameters. It has 8 aggregators and it has 32 leaves. So in the upper right corner, it's probably hard to see, but we have approximately 2 terabytes of memory available in the setup, right? So each individual aggregator as well as each individual leaf are the same x2 extra large instances. So if I expand them, so you can see that each node has 64 gigs of RAM and 8 cores. So right now nothing is really happening in the system. So basically everything is quiet. So this dashboard actually comes out of the box with MemSQL. So what it does basically right now shows you MemSQL has its own monitoring infrastructure. So what it does basically right now is just kind of monitors its own performance. And you can see this database that we're actually writing this data into. This is the monitoring data. Allows us to just basically insert 15,000 rows or 10,000 rows per second. Just basically our own internal monitoring infrastructure about MemSQL cluster. So what I'd like to do now is just to also just for a second get your attention here. So the IP addresses that we received from Amazon are scattered all over the data center, right? So these IP addresses you can see are different subnets. So what it means is that this cluster is really not really optimal for an inter-node data exchange. So some of the machines are all over the data center, so there's definitely more networking overhead while we having these machines communicate with each other. So this is not really optimal cluster, but for the time being, this is going to be working just fine for us. And in some cases, if you really have some high availability requirements, you can actually set up your clusters in different geographical regions. So you can actually set up some of your nodes in one geographical region, some other nodes in another region. We'll basically have geographical resilience in this case. So let me go ahead and start showing you some stuff here. So what I'd like to do next is I'm going to toggle a workload. So how many people are familiar with TPCH benchmark? TPCH, Transaction Processing Console benchmark. Some people are familiar with that. So anyway, so what TPCH is basically kind of like a benchmark. It's like a sample database, sample data, a bunch of queries, and a tool to generate more data. So this TPCH benchmark is frequently used by database, companies who basically analyze the performance of a specific workload on their hardware and software. So what we do is basically have a subset of data here, and we would like to analyze kind of the performance of the system. So the data, how the data arrives in MemSQL. Well, first of all, MemSQL has wire compatibility with MySQL. At the same time, MemSQL has a lot of other interesting things that make it easier to migrate from MySQL. So basically, we support the ability to dump the data from MySQL into MemSQL, and basically using the same tools for MySQL. So, but what now I'd like to do is just to show you a couple of things here. So this is just a console that we see here. What I'm going to do is just show you databases. So there are a couple of databases here. So the database that we will be loading data into is called MacData. So MacData is the database that basically will be receiving this data that we will be generating and inserting. So I'm going to say use MacData, show tables. So there are a bunch of tables here. So we will be inserting data in a couple of those tables. So specifically line item will be the one of the tables we will be inserting data in orders. So what I do next is I would like to kick off a workload that will be working on my 8 aggregators. So each individual aggregator also has a script inside that will be generating data and will be inserting this data into my MemSQL instance. Okay, every single aggregator. So right now I basically have 8 points where I'm inserting data. I have massive inserts. So let me just kick off this workload. So I'm just switching this button right now, and in a few seconds you should be able to see that right now my aggregators start working, and the number of rows that's being inserted is increasing, right? So right now in this cluster of 40 machines, I'm inserting roughly a little bit under 1 million rows per second, right? So how many people think this is cool? Yes! 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 This is awesome! Alright. So we inserting data, big deal, okay? What about querying data? It says, as we can see, everything right now is kind of busy, right? So you can see the CPU is growing. So we also see that the data in memory will be slow and steadily growing as well. As we leave this system for a little while, so we start accumulating data. So we still have 2 terabytes, plenty of space. We just let it run for a little bit, let it insert the data. So now, we're happily inserting all this data. Now, let's go ahead and query it, okay? So while we're inserting, let's go ahead and do some querying. So first thing that we'll do is we're business users, right? We'll write a query that will do what? We'll crash the server, right? No, we're not doing anything. So let's do a quick, let's see. Let's do a quick simple count from my. Let's see.
What?
Let's do count star from line item. Select, yes. Yes. So let's select. All right. So what I do here is, so we're waiting. All right. So right now we have approximately 79 million rows being inserted. Right? Let's run it again. It's 0.31 second, right? Previous query was about 6 seconds. So what we basically had here is the compilation time, right? That was we were compiling this data. Now, let's go ahead and insert a single. Control S. So right now I run it a couple of times. You can see every second or so we're incrementing the total number of rows in about a million. So let's do just a couple of things here. So let's, on the same line item table, let's just run a couple of abbreviations. And let's run a couple of max-min operations, right? So this guy is going to return also just a few seconds. Alright, so it's about 9 seconds. So the next, after compilation, we see it's 0.35 seconds. So see how much data I have right now. I have 125 million rows, and it starts growing, right? So, and what we do in this, we're basically going and just doing select. We're actually inspecting every single row, right? Now the cool thing about it is, we're using this technology called, basically we're using data structure called skip lists. Who know about skip lists? So very, very comfortable, very memory-friendly infrastructure, data structure. At the same time, very friendly for multi-value concurrent access, right? So you'll be able to multi-value concurrency control. We're familiar with MVCC concept, right? So the concept is you are trying to read the data as you're also writing data into the same repository. And in some cases, you may actually have two writers trying to write into the same row. So what you do in this case, you basically create versions, two versions in memory, right? You're not trying to hold the log for a specific row, which is operations will be, holding the resources, right? You don't want to hold any resources. You want to create concurrent access to everything. So in this case, if somebody is modifying something, you have to create a new version, right? So that's what you actually have to do. So as we know, if there is a resource that has to be shared, eventually it's going to become a source of constraint, right? A source of, and we can see it in a number of examples. So when we have a variety of different constraints on a shared resource, like my kids, for example, don't like to share toys. It's always a point of contention. Right, so anyway, so let's run a couple more queries. So let's run something more complex. So in this case, we're doing still a fairly simple query, just a join between orders and line items. So we have one-to-many relationship between orders and line items, right? So let's just do like an example of a reporting query. So reporting query also takes a little bit of time to compile, but second time it will go a lot faster. All right. So I probably inserted too much data already. It takes a while to go inspect everything. Bear with me. Not 25 seconds, okay. So it should be a little bit less next time. But right now we're probably operating already with somewhere in the neighborhood of 300 million rows. So it takes a few seconds to go and inspect all this stuff. So while we're doing this, so the second one was about 14 seconds. So another thing that's interesting here is this table that I'm actually inserting right now also has indices built in it. Right? So we also will be able to use indices and insert data into a table that already has indices built. So we do not need to do any index rebuild because everything is in memory. the system will be able to rebuild and reorganize indices automatically for you. So the next thing I'd like to do is, so right now what we've done is we basically loading the data, inserting data into the cluster, at the same time we're doing some simple read queries. So let's go ahead and create a query workload. Right? So the query workload will produce multiple concurrent connections, and we'll start creating massive reads against the data as it's actually inserting the data. So what I'll do next is basically go ahead and just switch this read workload. So while we're moving this data in a few seconds, we'll see that our read queries is going to have to start increasing very quickly. And what we have to pay attention to is basically how this massive read workload will be coexisting with my inserts. So right now we have approximately 3,000 read queries per second. And the queries can actually go against all the aggregators. I have 8 aggregators. If I need additional querying capacity, I can add more aggregators. But the idea here is, we inserting data and we at the same time reading the data. Okay. So while we're doing our reads, we see that number of rows that we're inserting did not really get affected in any way. So what it tells us is the basic system has extremely high concurrency. Right? So you're able to read data and write data simultaneously to the same tables, and a very, very high concurrency real-time access. Alright? So how many people this is exciting? No? Some people? Alright, great. So let's kind of take a peek under the hood a little bit more. So let's just stop this guys. Let's kind of talk a little bit about the internals. So right now everything quiet down. So let's take a look at the system. So inside MemSQL, so the same client access libraries that I use for MySQL, the client access library I'm just using here to access MemSQL cluster. So first thing I'd like to do is just basically take a look at all the setup. So let's say I'm going to go and say show leaves. So show leaves. So these are all leaves that I have in my system. So with all their respective IP addresses. So as you can see here, there is also availability group, right? So availability group tells me if the specific leaf is actually belong to, is it a master or slip, right? So you have basically the ability to say, hey, I have my leaves that are split up in 2 separate availability groups. And remember earlier I said that these availability groups can actually belong to totally separate instances of Amazon Cloud. For example, one cloud can be in a data center on the East Coast, another one can be a data center on the West. So they can actually be physically separate data centers to provide additional redundancy. So all the leaves are currently online, but if I go ahead and just take one offline, for example, plug a port out on that leaf, it basically will not produce any loss of data, the query will continue. So then you also can see show aggregators. So right now we have 8 aggregators. So one of the aggregators is called master aggregator. So all the DDL operations that you will be producing, DDL operations will have to be produced on master aggregator, and then it will be replicated across all the aggregators. So what happens if you lose an aggregator? Basically, it's not a big deal. You just lost one querying point. You'll have to basically reroute your connections to a different querying point. What if you lose a master aggregator? You basically have to manually have a DBA to say promote aggregator, and basically one of the aggregators in the system will be promoted to become a master aggregator. Okay. So another interesting thing I want to tell you about what's kind of running behind the scenes is partitions. So if I go and say show partitions, so inside, what happens when one of the leaves is being lost? So inside each database, there is a very smart caching algorithm that will basically tell you, okay, this specific database can actually be broken down into a bunch of different partitions. So a bunch of different partitions will be existing as a separate movable item on each individual leaf. In this case, we have actually number of leaves times 8 produces the number of total partitions in our system. Each individual partition, think of it as an independent data unit. It can be moved around anywhere in the system. So what happens is, if I have one of my leaf failing, I know for sure that all of my partitions on the 3 leaves have their redundant counterparts somewhere else in my repository, right? So with other leaves on my cluster, I always can find a bunch of leaves that will have the same partitions. So as a result of this, the system will remain online, and those partitions that you just lost on one leaf will be reactivated on other leaves, right? And then what you can do after that is say, now I would like to introduce, for example, you say, hey, my leaf that I just took down has data and I could not recover that leaf, right? So basically I have to rebuild the entire machine, and I can basically add it in as a completely new leaf with no data. So what happens in this case, you just run a very simple command that's called add leaf, and the system will automatically repopulate the partitions on the empty leaf. Okay? So that's like a rebalancing operation that's basically allows us to move the data, again, uniformly distributed across all the system. So let's see if there's anything else. So the idea here is, again, we want to make something that's very simple. If you look at overall code, it's really not that complex, but it does have some very interesting features to it. And the idea is really produce something that's very simple and very highly performant. It's designed from the ground up for performance. So that's kind of one of the sweet spots of this technology as compared to some other memory technologies. So right now the current version that we have for MemSQL is version 2.1, right? That you can actually download and start working with. But there's also version 2.5, which is coming out in just a couple of weeks. That version has some interesting features. You will be able to store JSON data natively inside the tables, and then you can query the data in JSON directly from the SQL query. So some people like databases that store data as documents. That's fantastic. So this is just yet another way of storing JSON-related content and make it very, very efficiently queryable in memory, right, for very high performance. So make it very scalable. So we're also working on the next generation product that basically will be released sometime in January. This is version 3.0, and that product will have multiple enhancements, including the columnar storage. So right now, everything that we're using right now is raw store-based, but we're also working reactively on delivering column store functionality very shortly. So at this point, I think we can probably take a few technical questions. If you guys have some questions. Eric is going to say something before you go.
Before we move on to the Q&A, I just want to first give him a great big round of applause to Nikita. First question.
I have two questions. One is in terms of, do you have any limitation in terms of the size of your database and the number of activities?
No, there is no hard. So the question is, do we have limitations as far as number of partitions and the size of the database? The quick answer is no hard-coded limitation. There are some practical limitations. For example, if you have database of size, let's say 1 terabyte, you need to take a look at the overall size of the cluster memory and basically have anywhere between 50 to 75% memory basically allocated to that database. So you obviously don't want to max out completely because there will be a certain amount of storage consumed by the query plans, right? Certain amount of memory. So, but overall, the rule of thumb is kind of like 50 to 75% of memory.
The second iterate to do is first is like already 5% is really accessible, like real time, and then 95% of data is really just more have time. So does your application support like access on the file, or every whole database you load to the memory?
Yeah. So the question is, do all databases get loaded into memory? Right, only the ones that are necessary, right? So the answer is all of them in memory, right? So all of them in memory, exactly. So, and basically the access to databases is just basically used through the same concepts, traditional, MySQL concepts like grant access, right? Grant access to objects. So basically the same security permissions that you would see in MySQL totally applicable here. So everything will go in memory, yes.
But maybe go over it again. How do you do the distribution when you're running a query to the ultimate leave and partition, how's that done? Is that a circular hash, like 160-bit type of circular hash that gets distributed, or is there something else going on there that I missed? And the number of partitions per leaf, in the maximum size of the cluster, like is that preset when you start your cluster? Can it grow over time as you add things to it? The number of partitions seems to be like the lowest level of partition. Like, does that grow? How does that work?
Sure. So repeat the question. Yeah, so the question, there are two questions. First question is, explain a little bit how the data distribution is working in terms of partitions. And the second question is number of partitions per leaf. Is it something that's can be changed? Can be changed preset and changed later? So the first question is how the data is being distributed. Data is being cached. So I'm not exactly familiar with the caching algorithm, but the idea is to basically you need to find a key that will have very high cardinality. It will have much higher cardinality than the number of leads in your system. And basically that key will be the distribution key. Right? So you will have to specify in DDL. Yes. So once you specify in DDL, I just did not show syntax, but basically on our website you can easily find that. So all the samples there, but basically you specify the tables, and the table can be, it's actually a very important concept. Basically tables that can be of two types. One table can be distributed, another table can be replicated, a reference table that we call it. Right? So distributed table will be a gigantic table, like in this case, line item was a very large table. The table will be cached across every single leaf. Right? So, and then there are multiple other smaller tables that can be replicated across all the nodes. And those tables basically can be joined to the distributed tables if you like to. Right? And then each individual join can be executed in a leaf independent of each other. Right?
And then the partition.
And the partition, right? And then the second question about the partition. So right now the system basically says, okay, so I have a number of leaves. I just multiply it by 8, and that will be my number of partitions, right? So when you create a database, you can actually control what the multiplier should be, right? And the rule of thumb here is that you want to really, if you have a large database or you have a system that has a large number of leaves, you probably would like to increase that number, right? And there are not like really hard and fast rules because it does depend on the workload, but you have total control over that number. And that number can be different from database to database. It's not for the entire cluster.
What is the distribution of latencies for a single row query?
So the question is, what is the distribution? What is the latency of distribution of a single row query? So if you're doing like a write, if you want to insert a single row, it's very, very fast. It does depend on networking, but it's definitely like it's a few milliseconds, right? So it's also extremely efficient. And what's also great about the system can be very efficient partition elimination strategy. If we have a query that actually can optimize a clue, some of the leads, basically where this data may reside, the optimizer will basically produce the query that will point you to a very specific lead. Right, and just grab the data from the feed.
Any idea what it would be for a read?
I'm sorry?
Any idea what it would be for a read distributed on 8 partitions?
Yeah, so I think for reads, reads can be of different kind, right, depending on the query. So if the query is very wide, in some cases you do need to have massive inspection of the data, for indices, for example, on every single lead. That may take some time. Like you saw in my example, I think I loaded probably like about, $500 million or so. So it may take 2 seconds, right? But we still believe that will be comparatively faster than anything else out there in the marketplace, right? So other systems that would rely on disk-based access will be faster than that. Question? Yes, go ahead.
The question's about the JSON database that you're building.
Huh?
How are you guys handling the parent-child relationships, and how are you going to index child and child keys?
Okay, so the question is how exactly we will be handling the indexing of parent-child relationship in JSON. So honestly, I do not know the answer, but I will give my card. If this is to respond, I will respond to it. Because this is new stuff to me still. I'm a relatively new employee. I'm putting my new employee card. But I mean, seriously, JSON is very important to us. We see so many great scenarios where people want real-time access to JSON documents, and basically this is very, very important to us. So we want to make sure we, as fast as we can, with that. So specifically how indexing for JSON works, I do not know, but I will get you an answer. All right?
My question was about indexing for JSON, so I would like to have your part. The second question is, you mentioned about durability. So are you providing complete durability or partial durability?
Oh, okay, so question is, are we providing complete reliability or partial reliability?
Durability, yes.
Right. So what's happening in the system is, it depends on the settings of the system. In the most reliable, durable way, what you can do is you can do redundancy is 2, right? That means that you will have every single row will be copied somewhere else in memory, some other machine. So that will give you at least redundancy in memory, right? And at the same time, you can turn on durability. Right? Durability means that that row will be physically hardened into, basically a sequential log file on 2 machines. So in this case, if you lose one machine, you still continue querying and inserting whatever. Nothing changes. That machine can be lost completely, or you can recover it because there is some data on the disk you can recover back from it. It can be possible, but data will be still hot. So if you lose another machine in the cluster, so the system is always resilient to a single point of failure. Absolutely. In some cases, it may be resilient to leaf failures. In some cases, you may lose half of the leaves, and you still won't function. It really depends on which leaves that you're losing. Right? So if you lose all the slave leaves, you basically will be able to, find the partitions elsewhere in the system. So in this case, you have a situation where the system can be resilient for worst case scenarios, single point of failure. It can be a lot more resilient than that.
I have one more silly question. Sorry about this. How do we compare MemSQL with MongoDB?
Great question. How do we compare? I'm about to find out. I'm running some tests. I will let you know. But we're trying to be very competitive. We're trying to be very competitive on querying as well as failover scenarios, right? So what happens during failover if you want to introduce another node and so on. So we're trying to stay very competitive. Yes.
I have a question on hot and cold. How fast can you take the data from cold? And is there a way you can push the data from cold to hot?
Well, see, in our case, in this setting, we kind of saying our data repository, main data repository is actually memory, right? And our cold data repository is that transaction log for durability. So, but we're really keeping it only for durability, right? So in our case, it's basically, these are 2 repositories that we have, but the main repository is the hot repository, right? So the secondary repository is the disk. So it's kind of opposite from traditional database designs.
But do you have a way to export data so it can be used by the other database, but not like MySQL?
Yeah, absolutely. So like the same, you can load like a flat file, you can load anything. So basically the same tools that we use for MySQL totally out. So in some cases you can load data in the aggregator, but we work with a couple of clients in New York City. They have so much data, like terabytes upon terabytes, they actually have to start loading data from leaves. Directly into leaves. It's a little bit more tricky, but it still can be done. So that we can work it.
What's the role of the master aggregator? And when it goes down before the admin brings up the new one, what capabilities lost?
Great question. So the question is, what's the role of master aggregator? And while master aggregator is down, what capability is lost? So ability to run DDL is lost, right? When you lose your master aggregator. So basically, if you want to create a new object, you need to have master aggregator being active, right? If you want to create, let's say, a new table, if you want to create a new index, or if you want to change the structure of the record. So, and until new master aggregator is being brought up, you will not be able to do that, right? But the remainder of the querying and everything else is happily happening without that. So, but then what basically happens is there is a DBA command to promote one of the aggregators to become the master aggregator and keep the primary repository of the DDL. Okay.
Questions?
Yes. Are stored procedures and subquery queries supported?
Okay, so question about stored procedures. So stored procedures, we don't really have a concept of stored procedures, and the reason for that is because everything is compiled into native code. So we kind of think of it like this is compiled code, it will be kind of like automated stored procedure execution, right? So once the query already run once, you already know it's already there in memory, and you can continue executing just the phone. So the big will stop working. Just not big storage, it's stop machine code object inside the database.
For other questions, Dimitri will be here for one-on-one questions. Thank you very much, Dimitri Chikatilo.